Hello students, welcome to EPG Pathshala. Today we shall be talking about the vector and raster based analysis of GIS. So as we have studied in the previous module, the basic concept of GIS is based on two features, that is the raster and the vector data model. The raster model is based on the grids or the picture elements, that is popularly called as pixels, while the vector data model is based on point, line and polygon. The point feature is a zero-dimensional feature that does not have any length, breadth or height. The line feature is one-dimensional and is used for representing linear features, while the polygon feature is a closed area feature. So in this module, we shall try to get an overview of the analysis that is used in GIS pertaining to the main data structures, that is raster and vector. Let's have a look. Coming first to the GIS system and function, the first one is data capture. Thus, GIS is a tool which integrates the data from various sources into a common format which can be compared and analyzed. The different input sources that are mainly obtained from manual digitization, scanning of aerial photographs, existing digital data sets, remote sensing based satellite images, and the global positioning system. The data storage and manipulation is an important step that is carried out after the collection of data. It is stored and maintained in the database and includes data security, data integrity, data storage, retrieval of data, and maintenance. The data analysis part is the most important aspect of GIS as it has an ability to interpret and analyze the collected information quantitatively and qualitatively. Coming to data presentation, it is also a very important function of GIS and is used to represent the data in a simple and a detailed way. The data can be represented in various ways such as maps, report and the three-dimensional images. Coming to the data models of GIS, the information within GIS consists of two elements, spatial data and attribute data. Spatial data is represented by points, for example, location of wells in a place, lines, for example, the streams, the road networks, and polygons, for example, soil delineation of mapping units of soil or grid cells. The attribute data or information that describes the characteristics of these spatial features is an important part of GIS. The spatial data are referenced to a geographic spatial coordinate system and are stored in a vector or a raster format as given by Burrow in 1989. The GIS platform stores and manages geographic data structure in a number of formats. The three basic data formats are vector, raster, and triangulated irregular network called as TIN. Now coming to the vector data structure. In vector data structure, the attribute information is always associated with point, line and polygon as spatial entities that describe the features occurring in the real world. The point is a zero-dimensional feature that does not have any length, breadth or height. The line is a linear feature, that means the breadth is negligible compared to the length of a feature, so it appears linear, while the polygon is used for enclosed surface areas such as a pond or a lake. Points are pairs of xy coordinates. Lines are sets of coordinates that define a linear shape with the width of the feature being negligible to the length. So, a line is made up of various points. The initial and the ending points are called as the nodes, while the middle points that constitute the line are known as the vertices. Polygons are sets of coordinates defining boundaries that enclose areas. Coordinates are most often pairs of xy or they are triplets, maybe x, y and z, where z represents a value such as an elevation. This kind of representation of the world is generically called a vector data model. For example, a point representing a town associated with its population, the number of houses, and the number of hospitals, and so on. A linear feature such as river represented by line is associated with name, mean discharge, and so on. A land use represented by polygon features is associated with its past land use, soil type, soil moisture, etc. The vector data structure is categorized into spaghetti data structure, topological data structure. The spaghetti data model is the most simple data structure. In this model, each entity on a map becomes one logical record in digital file and is known as a string of XY coordinates. The spaghetti vector data structure is not optimal because it does not take into consideration shared lines and points. All identity is defined spatially without any spatial relationships. This creates limitation to perform any types of spatial analysis. The spatial relationships of entities are obtained through computation. Different lines and polygons are stored as independent objects in this data model. Lines between adjacent polygons must be digitized and stored twice. Okay, so now coming to the next data structure, that is the topological data structure. It is the most widely used method to reveal spatial relationships. For example, an area or a polygon is defined by a set of lines which makes up its boundaries. In this case, the line is the border between two polygons. Each line can represent part of a path connecting other parts. For examples, line can be used to represent streets and the routes. The connectivity of these features is referred to as their topology structure. We also know that topology refers to the spatial relationships between the objects. The topological mathematical tool is used to define spatial relationships. The model is also known as line arc node data model. The advantage of this model is data redundancy, which is reduced because of shared nodes and lines which are stored only once. Attributes are linked to each feature. The attribute data is stored in separate relational tables. Therefore, more files are maintained for this purpose. The database management system is used, which provides more efficient access in this type of data structure. Coming to line or arc, it is a series of points that start and end at a node. Node is an intersection point where two or more lines meet. Node can also occur at the end of a dangling line that is not linked to another line. The polygon is comprised of a closed chain of lines that represent the boundary of the area. The point is encoded as a single xy coordinate pair. Point is considered as the polygon with no area information. Now coming to the properties of this topological data structure, the first one is connectivity. This property indicates which geographical features connect to others or which geographic feature intersect each other. For example, line 1 is connected to line 2, 3 and 4 in this figure. The next property is adjacency, which indicates which geographic features, that is nodes, arc and smaller polygon, are contained within polygon. For example, the polygon D is inside the polygon B in this figure. The third property is containment, which indicates which geographical features, for example node, arc or smaller polygons, are contained within a polygon. For example, in this figure, polygon D is inside the polygon B as shown in this figure. Now coming to the advantages and the disadvantages of these vector models. There are various advantages of vector data model, such as it is precise and allows no error in line, area or perimeter. It requires lesser storage as compared to the raster format. Further, this method is more appropriate for social, economic, demographic, and resource variation analysis. The disadvantage of this data model is that it takes too much time in computing for overlaying the vector information, and it cannot represent any continuous data. The next one is the raster data structure, which divides any area into regular grids in a specific sequence. It is generally sequenced row by row from top left corner. Each cell of a grid contains a single value. In most cases, the values are to be assigned to each and every grid in the raster data model. It is often coded as ASCII format. It is relatively a simple approach for data integration, both conceptually and operationally. Digital elevation model uses the cell by cell data structure because the neighboring elevation values are rarely the same. Satellite images also use this method for the data storage. The advantage of raster GIS model is that it is easier to interface with the remote sensing images. This figure shows us the cell by cell data structure record, wherein each cell value by row and column is represented in the raster data model. The advantages of raster data structure are that it quickly processes the queries and the most analytical operations such as overlay, buffer, proximity, and Boolean queries. This model is also good for representing continuous surfaces. Raster data formats are appropriate for remote sensing data. It is easy to understand, read, write, and draw onto screen. However, the disadvantages also cannot be overlooked, such as this format is poor at points, lines, and area. It uses pixel based data processing, which affects the accuracy, especially for point and linear features. The lines can become broader. It is good at localized topology, such as adjacency, and it's weak at others. This format faces mixed pixel problem, which creates the problem in identification of different features. Each cell can be owned by one feature, and the greatest disadvantage is that it requires very high storage space. So some examples of vector data analysis include selecting feature by location. This involves spatial joining and location queries. In most of the times, it is quite useful to join attribute information from a polygon map to a line map. Moreover, one can also select a subset of features based on their location. The next is buffering and overlaying. Buffering includes the selecting feature by location tool, which is designed ultimately to select a unique subset of objects from different map layers. However, in buffering, we analyze spatial data layers in a way that creates entirely new objects. For example, let's imagine that we want to determine all those areas in India that are not within 50 kilometers of an interstate but are within 25 kilometers of a river. We can do this by buffering the interstate at 50 kilometers and overlaying the area outside the buffer with the area inside a 25-kilometer buffer of streams. The next example is overlaying. For this, suppose we need to overlay the two buffers to identify the areas outside the road buffer and inside the river buffer. In this, the overlaying method is quite useful. Another example is feature manipulation for vector analysis. It includes clipping and dissolving. Clipping is used basically to clean up our analysis. We can remove non-Indian areas. In this particular context, it is known as clip. The next is dissolving. This is used in a case where we find a situation where many different neighboring polygons have the same value. Since the polygons share a common boundary, There is no reason why they can't be dissolved together into one bigger polygon. This situation is illustrated in this figure, which shows many different polygons with similar values neighboring to one another. The examples of raster data analysis are also varied, such as the display of digital elevation model, popularly known as DEM, the calculation of slope, calculation of aspect, the hill shade, calculating any view shade, neighborhood statistics, zonal statistics, extraction by mask, distance buffer analysis, reclassification, vector to raster conversion, using the raster calculator for various mathematical operations such as adding, subtracting, averaging, and so on, and raster to vector conversion. As GIS includes both attribute and spatial data, the study can be conducted on both the data types. Thorough analysis of these data models reveals new information about the spatial features. In vector data structure, attribute information is always associated with point, line, and polygon as spatial entities that describe features occurring in the real world. However, in case of raster data, grid and cell values are used to retrieve information from spatial data. These types of analysis are very useful in getting information from the data models and make the data easy to understand by segregating different features present in the data. As you all know, this raster data model applies to any data that represents continuation, such as elevation, soil moisture, soil types, or soil mapping. Also, the vector data model is used for point features, line features, and polygon features. We have discussed the dimensions of these features and what are the various data structures used for both vector and raster data. We have also studied the application of these data models in various domains of GIS. I hope you all will learn from this and be benefited. Thank you.